Hello everyone, welcome to my channel. In this video I am going to discuss the topic magnetic field and Lorentz force from the chapter moving charges and magnetism. Now prior to this you have gone through the chapter electrostatics, wherein we have seen that if you have a static charge, but the static charge produces an electric field. Static charge produces an electric field. Now here we will see that a moving charge or a current, it produces a magnetic field. Okay. Now this chapter studies with the motion of charge under magnetic field or charge producing magnetic field, how this magnetic field affects the motion of other charges or conductors. So in this regard, the first topic is study of this Lorentz force. Now if a charge Q, it is subjected with electric field E and magnetic field B, then the force on this charge is the vector sum of force due to electric field and force due to magnetic field. Okay. Now, so this force is called the Lorentz force. Okay, so Lorentz force, it is basically the force on a charge under simultaneous influence of electric field and magnetic field. Okay, so now we have electric field and magnetic field simultaneously acting on this charge Q. Now force on the charge due to electric field, suppose E is the strength of the electric field, then force due to electric field, this we have already studied, it is QE. Okay, this we have already seen in the chapter electrostatics. Charge on the positive, force on the positive charge will be in the direction of electric field, force on the negative charge will be opposite to direction of electric field. All those things you have already studied. So this is the force on the charge due to the electric field. Now force due to magnetic field, this force is called magnetic Lorentz force. This force is called magnetic Lorentz force. Okay, so now this we have already seen. Now let's see what is the form of this force. Now suppose you have two mutually perpendicular planes. This is one plane, this is another plane. So these are two mutually perpendicular planes. Suppose this is your x-axis, this is y-axis, and this is z-axis. Okay, and this is the origin. Now suppose at origin you have a charge plus Q, it is moving in this direction with velocity v, and this is the direction of magnetic field. Okay, now Lorentz, what he observed that the magnetic force, magnitude of this magnetic force, it is proportional to the magnitude of the charge. Greater the charge, greater the force. Okay, now suppose this is the velocity vector and this is the magnetic field. These two vectors are lying on this xz plane. This angle is theta. So theta is the angle between the velocity vector and the direction of magnetic field. Now it is also observed that this strength of the force, magnitude of the force acting on the charge, it is proportional to strength of the magnetic field. Greater the strength of the field, this is the magnetic field, so greater the strength of the field, greater is the magnetic Lorentz force. And this strength of the force, it is also proportional to component of velocity vector perpendicular to the magnetic field. Okay, now if this is V, this is theta, component of V, this is B, this is V, and this is theta. So component of V parallel to magnetic field will be V cos theta, and this will be V sin theta. This component is perpendicular to the direction of magnetic field. So V sin theta will be in this direction. V sin theta is perpendicular to direction of magnetic field. So I can write this as force proportional to V sin theta. Okay. Now this was experimental observation, and from combining all these results we get FB, magnetic Lorentz force, proportional to QB into V sin theta. Now this proportionality constant, this appears to be 1, so this term FB can be written as QVB sin theta, and in vector form this is written as FB is equal to Q V cross B. Okay, so that means force, magnetic Lorentz force, will be the direction of V cross B. Now if you apply right hand curl rule, the cross product rule, this is V, this is B, so V cross B will be in the direction of this vector along y axis. So this is the direction of FB, magnetic Lorentz force, provided, okay, provided this charge is positive. This charge is positive. If this charge is negative, you will be getting FB equal to minus Q V cross B. So in that case, the force will be in the downward direction. Okay, so this is the expression for magnetic Lorentz force. So Lorentz force expression was this Fe plus Fb. So Fb we have now obtained. So combining these two, we have F is equal, see, F is equal to Fe, force due to electric field, plus force due to magnetic field. So this is F is equal to Q E, force due to electric field, plus Q V cross B. So that gives F is equal to Q E plus V cross B. So this is the expression for Lorentz force. Okay, this is Lorentz force, and this is magnetic Lorentz force. Magnetic Lorentz TZ force. So since we have obtained the equation for this magnetic Lorentz force, let's see a bit more about this expression in a bit more detail. Like, first thing is, like, if Q is equal to 0, magnetic Lorentz force will be 0. That means a uncharged particle moving in magnetic field will not experience any force. Uncharged particle in magnetic field, moving in magnetic field, will not experience any force. Then if V is equal to 0, again magnetic Lorentz force is 0. That means if a static charge in a magnetic field will not experience any force. Static charge in magnetic field will not experience any force. Then see this expression, magnitude of this expression can be written as Fb is equal to QVB sin theta. Okay, now for theta is equal to 0 degree or 180 degree, again magnetic Lorentz force is 0. So that means, what is theta? theta is the angle between the velocity vector and the directional magnetic field. So if the velocity vector is in the directional magnetic field or anti-parallel to directional magnetic field, the charged particle will not experience any force. Okay, so these are the conditions under which there is no force on the particle. Okay, now another interesting thing is, see this force here, FB is Q V cross B. That means this force is perpendicular to the plane containing V and B. Okay, now since so FB is equal to Q V cross B. So this implies this magnetic Lorentz force is perpendicular to velocity vector. It is also perpendicular to the direction of magnetic field. Okay. Now since magnetic Lorentz force is perpendicular to the velocity vector, it implies magnetic Lorentz force is perpendicular to displacement of the charged particle. Now since the force is perpendicular to displacement, work done by magnetic field or work done by magnetic Lorentz force, it will be 0. Why? Because work done by magnetic Lorentz force will be FB dot S, but force and displacement, they are perpendicular, so this will be FB S cos 90 degree, that is equal to 0. So that means work done by magnetic Lorentz force is always 0. Okay, so what does that imply? From kinetic energy theorem or work energy theorem, we have work done is equal to change in kinetic energy. Okay, so since work done is 0, that means change in kinetic energy is 0. So that means kinetic energy of a charged particle moving in a magnetic field, uniform magnetic field, will not change. Kinetic energy will not change. That means speed will not change. So since there is no change in kinetic energy, speed of the particle remains constant. Speed of the particle remains constant. Now you may ask, if there is an action of force and there is no, so speed is constant, how is that possible? See, force does not causes changes in speed, force causes changes in velocity. Okay, now since speed is constant, that means magnitude of velocity is constant, but magnetic Lorentz force will cause the charged particle to undergo a change in direction. Okay, so how it changes the direction of charged particle, that I will discuss in the next video, but these are the basic things with regard to the magnetic Lorentz force. Work done by magnetic Lorentz force is always 0 because magnetic Lorentz force is perpendicular to direction of velocity, hence it is perpendicular to direction of displacement, so work done is 0. So since work done is 0, there is no change in kinetic energy and speed of the particle remains constant. So these are the few basic things related to the Lorentz force. So this is the introductory video to the chapter moving charges and magnetism. I will prepare the rest of the videos based on feedback received from you all. So good luck and my best wishes to you.